Bismillah ar-Rahman ar-Rahim. Continuation for the calculation of the electric potential. Dr. Makki just finished finding the electric potential due to a pointed charge, and he said V equals KQ over R if you have a pointed charge and you want to find how much is the electric potential at a distance R from that pointed charge. We said V at this point P equals KQ over R, and this V is a scalar quantity, will be positive if the charge is positive, and it will be negative quantity if the charge is negative, okay? And this electric potential will decrease as a function of 1 over R. Now, what I'll be discussing in the next few minutes will be the electric potential due to an electric dipole. You remember from previous videos what is meant by electric dipole. Electric dipole is a negative charge and another equivalent positive charge separated by a small distance d, okay? This will form what we call the electric dipole, okay? Now we are interested to find how much is the electric potential at a certain point B very far, okay? So meaning that the distance from the center of our dipole is very large when compared to d, which is the separation between the two charges, the negative and positive charges. This is the meaning of large distance. Large distance meaning that this distance, which is R from the center of the dipole, is very big compared to this d, okay? By the concept just discussed by Dr. Makki, if you have multiple charges and you want to find how much is the electric potential at a certain point, will be the algebraic sum of the electric potential of each one, okay? So V at point B, this is point B, due to electric dipole will be K, okay, multiplied by Q divided by the distance from the positive charge, which I call it R plus, okay? Summation, so this is algebraic sum with the electric potential due to the negative charge at point B. And this will be minus Q divided by the distance from the negative charge, which is R minus. I call it R minus, okay? Let us simplify the situation here. So this is Vp equals K Q multiplied by R minus minus R plus divided by R minus multiplied by R plus, okay? Let us have some approximation. If this is very large compared to D, R minus for R, which is very, very large compared to D, we will get the following approximation. R minus multiplied by R plus is approximately R square, okay? So going very far, we can approximate this multiplication. R minus multiplied by R plus is approximately R square. There is also another approximation. So here we can replace R minus multiplied by R plus with R square, okay? And the difference between R minus and R plus, which is this much, okay, this distance, which is the difference between this long distance from the negative charge and the shorter distance from the positive charge, here we can complete the right angle triangle. This is one side of it, which is the difference between R minus and R plus. This is 90 degrees, okay, and here we have the distance D. If this angle is theta, this is approximately theta because of the large R compared to D. We can, from trigonometry, tell that this separation R minus minus R plus is approximately D cosine theta. So this is approximately D cosine theta, okay? So now I can simplify the situation. Vp, the electric potential due to electric dipole at point P will be equal to K Q multiplied by the difference, which is D cosine theta divided by R square. But what is QD? QD, we have seen this before. It is the magnitude of the electric dipole. So this will be Kp cosine theta divided by r squared. What is r in this case? It is the distance from the center of the dipole to the point where you would like to find the electric potential. Okay, so this potential, what do you notice about this potential? Is it always positive? Is it always negative? What do you think? It will depend on the theta. If the angle theta between 0 and 90, this will be positive, meaning that you are here in this region, okay, in the vicinity of the positive charge, closer to the positive charge, electric potential will be positive. If theta is 90, meaning that you want to find V at this point, will be how much? Cosine 90 will give you 0, and the electric potential will be 0. Why? Because you will be at the same distance from the positive charge to that of the negative charge. So you will end up with KQ over R and KQ over the same R, negative sign, and you will end up with VB equal 0. If you come at these points, you will be in the vicinity of the negative charge, and you will be closer to the negative charge. As a result, the cosine here will give you a minus sign, and you'll end up with VP negative here in these regions, because theta in that case will be greater than 90 in the second quadrant. So cosine of an angle in the second quadrant will give you a negative value. So this is very nice result, and it tells you about the electric potential due to an electric dipole. Thank you. Now it is time to try to calculate the electric field from our knowledge of the electric potential. Previously, in previous videos, Dr. Makki has shown to you that we can calculate the electric potential from our knowledge of the electric field. If you know the electric field, you can find how much is the electric potential. And he said that the electric potential equals minus the integral of the dot product of E dot ds. Okay? We can write this equation in differential form. dV equals minus E dot ds. Okay? So this can be written as ES, which is the component of the electric field in the S direction, is nothing but minus the change of V with respect to that S. Let us say it in the X, Y, and Z. So the component of the electric field along the X-axis is nothing but the derivative or the partial derivative of the electric potential with respect to X. What do you mean by this partial derivative? It means we will consider that X is the variable, and other Y or Z will be considered to be constant here only. And the Y component of the electric field will be minus partial V partial Y. The rest, X and Z, will be considered to be constant, okay, when you make this derivative. Here, Y and Z will be considered to be constant when you take the derivative of the potential. And this is the Z component of the electric field will be minus the derivative of the V with respect to Z, and we consider that X and Y to be constant. Okay, this is the meaning of the partial derivative, my son, because I know you didn't cover it yet in the math course, but here in physics, this is the meaning of the partial derivative with X, partial derivative with Y, partial derivative with Z. We consider the others to be constant. And inshallah, in the examples, this will be explained. So we can write this in words that the component of the electric field in a certain direction, in any direction, okay, is the negative of the change or the rate of a change of V, which is the electric potential, in that direction, or with respect to that direction. With respect to that direction. This is the meaning of these three equations, but in words. Let us have a special case. If the electric field is uniform, if E is uniform, what will happen? Here, E will come out of the integration. So this will be V equals minus E dot the integral of ds. But what is the integral of ds? We'll get delta S. So we'll end up with E equals minus delta V over delta S. Okay? This is a special case when you have the electric field is uniform. Of course, in the examples, inshallah, we'll try to give you several examples. One in which we have non-uniform electric field, where the electric field is changing along X, Y, or Z. And another example, inshallah, when the electric field is uniform. Thank you.